Well, first, thank you very much. I would like to thank the organization for the invitation. It was beautiful ceremony Monday. Adriano said some things about me that was very, very important for me because, you know, when somebody says something wrong about you, you don't believe. But when somebody says nice things about you, you accept directly. So that's what I do. Thank you, Adriano. Well, we have a group in São Paulo, and you can see we have the doctor to treat us. You know, first one, psychiatrist. The second one is the boss of the psychiatrist, Eri. The red ones are the ones that wrote this paper. The other ones are the ones that wrote the other paper that you saw yesterday. Okay. I also was there, and Victor also. I'm going to talk about something very interesting, that is the balance of clinical trials, balance between the arms, okay? So, to show what is a real balance clinical trial, this is my wife's sister. They want a couple of Dobermans. And she likes brown, and he likes black ones. She likes females, and he likes the males. So they have a couple, and they had 8 little ones. And the 8 little ones, we had 2 brown males, 2 brown females, 2 black males, 2 black females. So this is the real balance, the completely balance for these born little ones. So if you look here, you have 2, 2, 2, 2, okay? This is very nice, because if you want to do an experiment with these little ones and to have, to look for their lives, you know, you can divide in 2 arms. One looking for one way to grow up, and the other another way. And you see the result by looking for something. And how do you do that? Well, you go here and take one to each side. The other, and everybody is going to do that. But if you do randomization, suppose that we have to choose one by one, and you have to put the one that is in your hand in one of the arms. How do you do that? You know, so you don't have the final group. You have to born one and send to one place. Born another, you send to other place or the same place. So you have a problem. You cannot have the complete balance when you do one by one. Another thing is that, suppose that you want to choose randomly the 2 arms, for example. To get something like what I am saying to you, one to each side, the probability to have something like that is just right, it's very little if you do the randomized experiment. So that's why we think that we need to do something before the experiment begin, okay? And our problem starts with a very complicated clinical trial. In a psychiatry department, we have an experiment that every week we got 3 patients. 2 goes to one side and 1 goes to the other side. And we have to do the allocation for those guys. And every week we have to do that and look for the other ones that were in treatment. And also, we have prognostic factors that had to be in consideration. For example, we don't want to see that there is external influence on the result of the experiment. So we try to do our best to control what we want, what we know, okay? And somebody says that I am against randomization. I'm not. I say every time when you have to randomize, you randomize, not because it's going to solve your problem, but you can say, if I don't randomize, something wrong happened, it's your fault. But if you randomize, the fault is of the coin, not yours. So that's the reason you really have to randomize, my opinion. Okay, so this is a very interesting example that what is balance. So we are looking for that. Okay, in our group we have another paper that is coming now with this title. Is this one here? This one here is the one we are talking today. It's going to appear in a clinical trial journal. And there is another one from Professor Júlio, who I believe is coming also in a good journal. So our group is really fighting half from one side and half to the other side. So we discuss a lot. So we have to write to defend ourselves, and this produces a lot of work, you know, how this works. Okay. So the objective of this paper is about the OCD. OCD is a psychiatric problem. And we have patients in the clinic. We have to choose how to allocate the patients sequentially. All right. I had to do this a long time back. And I have the results of our allocation. That's what I am going to show to you. But before that, I am going to say how we have done that. It's a very simple idea. You know, one thing important, it's every hard thing you have to do, you give to your students. The easy ones that you take for you. Is that right? Yeah? So that's what we have done. So I present this here because it's the easiest one. Okay. You're going to see how nice are the final results of the balancing. Here we have the explaining the experiment, but we don't need to know here because there is no doctor here, so I'm going to jump forward. It's an explanation here. In psychiatry, you don't have too many patients they like to go to an experiment like this. It's very hard to get the. For example, I'm doing an analysis now with yoga. Suppose the guy has OCD, and you tell him that he doesn't have to take drugs. You go to yoga, and you can be better than the ones that take the medication. It's not everyone who wants to do that, you know. So it's very complicated to get the sample. Before I start with the real experiment, I would like to show you how we decide to do that, okay? It's we call intentional allocation. Suppose we have a prognostic factor like age. So you remember the little ones, the little dogs? Everyone have the same age because they were born the same time. And I have browns and everything is balanced there. So it's a perfect balancing. So we would like to have this for the human patients. Okay, so suppose we have 2 arms. One with 15 patients in treatment 1, and in treatment 2 we have 17. There is a new guy coming here. So I have this, I'm going to consider the age. So the guy is coming, the new patient is coming, and I have 3 categories: the young ones, the adults, and the old ones. And we have this for the first arm, and this here for the second. We don't have to have a proportion, because with the Atkinson distance, it's only compositional distance. I don't measure the distance between 2 vectors, but I measure the distance of the composition of the 2 arms. So I'm going to talk about this soon. So what do? We consider this guy going first to this line and take the distance between these 2. And then we take him out and put him here and take the distance. The arm that gets a smaller distance is where I'm going to put the guy, okay? So that's simple like that. So when we have here, we call A1 star, so I increase 1 and have this one here, okay? The other one is the same. Then I take him out and put in this arm, and you come to this place here. You look that here we have the sample of this arm is much bigger now than the other one. Was 17 and 15, now it's 18 to 15. It increases this sample. And then I take the distance between the 2 arms, and the distance becomes, I'm going to show you what is standard deviation, you know. In fact, we have the log of the ratio and take the standard deviation of the vector, of the elements of the vector, okay? So, what is the distance? I have A1 is, I don't know why this happened here. Well, it's A11 to A1K and A21 to A2K. K vectors of composition of frequency. I define this log ratio, which is the log A1 minus the log of the other one. L is the mean of the log of the ratio, and we take the standard deviation of this random variable. So we take this random value now, and we take the standard deviation of that. So this is the Atkinson distance. Only to check if it's okay, let's see here. I have this vector and the other vector, and multiply by 2 this to 1. This also I multiply by 2 and keep the other one. And when we take the distance, Atkinson distance is going to be the same. If you take the Euclidean distance, it's going to be very different. So here I am measuring it's something wrong here. They are different. I did a mistake when I compute this here. But you see, I am only measuring the compositional distance of these vectors, okay? So what do we do? The guy comes and have a rule here. We have a factor, it's categorized, classify patients already enrolled, calculate relative frequency in each category, consider adding patients to a treatment arm, find new relative frequency A star, calculate Aitkinson distance, and then we do this for every prognostic factor. We could mix to them, but I'm going to show you that it's better to do this when the doctor have some prior opinion about the importance of the prognostic factor. And then our study goes in 2 steps. The first step, we have 2 arms. The ones that did not respond to the treatment are divided in 3 groups. Então, the phase 2, we don't have, in fact, the sample here is a little bit, they say 40, I have to have 40 people without responding the treatments, okay? So, here is the final response. The final response is the measure of some psychological points, O and C measurements. Usually they sum this, and since they are very correlated, we have defined a way to measure, I believe it's better than the other one. When they sum the dimension, the 2 dimensions, and goes from 0 to 40, I believe we have to take the maximum between obsession and compensation. Okay? So we define another measure here to improve a little bit the measurement. We have a paper about this. So we have really defined this. It's a journal called Medical Express. And we had produced this paper. Also with Victor, where is he? Oh, here. Okay. Well, in our experiment, we have many prognostic factors. For example, age, the first measurement of OCD, the gravity, so it's less than 8 and 15, and high is over 15. No previous treatment, we have 2 or more. No previous treatment, 1 course of previous treatment, 2 or more. We have level of education, marital status, gender, and sample size. I'm going to include sample size also in the distance in order to control the sample size. So we have factors to be balanced. We have current age, OCD, as I told you. And the OCD is the one that have more categories. We have low, 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 medium, low, high, medium, low, medium, medium, etc. Now, if the guy is low, low, he is considered not having the problem. So he doesn't have OCD, okay? So this category here is not going to come to our experiment. Treatment history and etc. 4 category for level education, marital status 2, and for sample size we have a little bit the distance between N1, N2, and N2, N1. So we reverse this and want to have the minimal distance, okay? So this is also an important part of the experiment, to control the sample size of each arm. And then we have the many distance for every prognostic factor. And then we will, in the first stage, we weight the distance to, and actually, in the first step, we don't control the sample size. It's only in the second step. Sorry for that. So my distance in the first step will be 2 for age, 3 for OCD, 3 for history, and 1 for gender. That's defined by the psychiatrists. In the second step, we consider more than, we consider scholarity, marriage, gender, and sample size. And sample size here is very important. It has weight 5. We discussed these weights, we discussed a lot how to put this. In this new paper, we have a big discussion about the weights that goes to each prognostic factor. Well, in phase 2 we have 3, and finally we have, if you have 3, I'm going to take the distance 2 by 2, have three distances, and we take the average of the 3 distances. So it's a more complicated, a little bit more complicated. So those are the results. I want to show you that what is here is the real observation. And here is when I reverse the order of the entrance. We had done this for many orders, but I realized that in the paper we had to have only the reverse the entrance. And you see how it's coming here. 7171, 4949, 53, and 38. That's different. So we have some difference here. And very close to the other ones also. Okay? Now, those are also the division for the arms, and you see we have little people with this situation, little one with this, that goes very up here. So that's the most common ones. And you see that it's very close to each other here, very close to each other. Okay? So the proportion, you see the proportion is more or less the same. Huh? I guess. All right here also. And also here. No? So the balance is very nice. That we have compositionally very nice allocation. Okay. Here are the other ones. I'm not going to talk to this, but if you look at the proportion here, you're going to see that they are very nice also. See? 133, 167, 67. And also here, if you look at this, 3 things here. So it works very nicely. What happened was when we reversed the order. The balancing is exactly the same, you see? But 65 people change place from one arm to the other. But the balancing is exactly the same, as you can see, okay? For the 3-1, it's a little complicated, but if you look 5 and 6, 10 and 9, 9, 9, and this is the ones that are kept in the same arm as before. Okay? After we have done this, we published the paper, and people look for the criticism. What could happen if we do intentional allocation? Maybe some doctors think in a bad way could take one of his patients and only send the patient after some time because he knows how to do the computation. So Professor Julio went after Bazou's papers, and he looked at this here. The choice of a purposive plan will make a scientist vulnerable to all kinds of open and veiled criticisms. A way out of the dilemma is to make the plan very purposive, but to leave a teeny bit of randomization in the plan. So how he has done that? It's like this, not exactly like this, because it's a little more complicated. But it's like the guy comes and you have a randomized mechanism with probability. Very small or half. Suppose you have a mechanism and you use the mechanism to tell if the guy goes for randomized or if the guys go to the intentional. So the external people doesn't know what will happen with, if you increase this probability, more and more uncertain it will be the allocation. So that's what happened with that particular paper we have written later. And now, oh, it's not good here. I can show you there. Here we have a new patient, the yoga experiment. We have two kinds of yoga, and we want to show that one of them is better than the other. If we had the full people in the same place, I could look directly in the classification and choose here one to one arm and the other to other arm. In this one, you take one hip on here, and then you choose one to each arm. So you could do the optimal allocation by only looking at this table, okay? This is the best allocation you would have with two arms. You would be dividing these cells in the two experiments. So we have randomized the order, about 50,000, I think, and we start to study how we perform with the intentional and with the epsilon, changing the epsilon from 0 to 1, okay? So, in this new experiment, we could, we had the original allocation, the original order, and we were very lucky because our sequential allocation was exactly the same thing that, exactly not changing a little bit the distribution, but exactly how the optimization for the whole people would do for the balancing. So in fact, by doing sequentially and working like we did, we could have a very good allocation, really very good one, this one. And I'm analyzing the experiment now, and the hard criticism is how to do statistics when you have intentional allocation. And then I tell the people that randomize, and I tell them, is my allocation a special case, a sample point of the randomization? And they say yes. So if you do randomization, get my allocation, can you do statistics? Yes. So I can also do, because it's the same sample point. And that is the real complication in our reflection about the results of the experiments. Okay, so let's see after we do a simulation, let's see what happened with the empirical distribution. Here is the black one, is our intentional. And here are the many epsilons up to the complete randomized experiment, which is the low one. So we can show that the distribution for the intentional allocation is much better, not much better, but a little better than the other ones. I say a little better because we have in this experiment nice sample, 50. Is 25 to one side, 25 to the other, or a little bit different, but it's like that. So our sample is not very large, but is also not very small, to be fair with the comparison we are doing here. So we were very lucky because we have exactly 50 patients to do the yoga, the two kinds of yoga. So we could do all this work before the experiment starts. Now we lost a lot. You imagine that the guy had to stay 2 years in this treatment. And so the people leave the treatment because if they improve a little bit, they go to work, they go to do something in their life, okay? This graph is not good, but this is the percentile picture. You see that our intentional sampling is low here, so it has a smaller distance than the randomization experiment. Okay. I'm finishing, almost finished. Okay. Now, one of our friends goes after something because he likes to fight with Professor Julio. And he went out to see what was the first randomized instrument, which is a very old one, and discover that there is in Kyrgyzstan. This is in the Kyrgyzstan country. I never know that we had a country with this name, you know. So, and he wrote a little tale saying that Professor Julio went there to check if how good was the lottery in that place. And also in our paper we put this photon. You can't see very much here, but it's very, very interesting thing. So you are going to see in the paper. Now, what happened with our simulation? And you're going to see that we don't have 50,000. We don't have 50,000. We threw out all the samples with less than 20 subjects. So we threw out, if one arm has less than 20, we threw out not to have any tendency against one of the allocation kinds. So you're going to see that why I have here a credible interval is because the referee asked us to have that, but you don't have to think about that. You don't have to have that. But if you want, we do, because it's not difficult to have. So, the proportion of times, the proportion of times that the intentional allocation, it's better than the other kind of allocation with epsilon equal to 0.1 is 54, and is going up to 60, and you see that's not very much different. So you can do randomization when you have a large sample. I believe that it's not going to disturb a lot. So here with this simulation, we can see that with the intentional allocation, we can perform better than with randomization. Here, we have H and 20, 20, 32. Yeah, I think it's the. I think this is the vision at the end of our experiments. It's a little bit. We have 50. If you take the sum here, we have exactly 50. 18 plus 32 is exactly 50 people. And now I'm comparing with the global allocation. With the global allocation, we have 15 in each side, 10 here, and exactly the same allocation. That is the same as in the global global allocation. Global allocation we call when you have everybody in the beginning and you can divide the whole sample in two parts. Okay? Looking for them. Okay. That's exactly what I had to do and to discuss with you. This is real Bazoo's kind of, isn't it? he usually talk about randomization this way. Let's only tell you that Bazoo is known by his theorems, but also the discussion about randomization. There was a Congress in Washington, and the organizer was a very, very famous one. And he said, sampling is divided in two steps, before Bazoo and after Bazoo, because of the paper he wrote in that particular seminar. Thank you very much.
Thank you for a nice talk. Now, I see lots of hands. Okay, let me give, first of all, give them.
Hello. How difficult was to measure the weights?
The first?
The first one, the final.
The first one, Vito put some prior numbers there. He usually put 1 and 1 and start from there and do the allocation. You can, it's exactly, you give the same, when you give the same distance, you randomize.
No, I mean the weights that the psychiatrist gave you for the final.
I did not.
Two weights, the weights for each of the prognostic factor.
Each time. In each step, you weight the factors.
But you have to ask the psychiatrist.
Yeah, yes.
And was this difficult to get the answer?
No, you see, when somebody comes to your office, you know if it's a woman, if it's a man, if it's a height, it's old. So it's the characteristics of the person. So you don't have problems with that. The one thing you have to do is to take the questionnaire when the guy comes to treatment. You have to do to apply the questionnaire, the instrument to measure them. Okay.
So there is a very important paper in the theory of randomization written by Fernando Bonassi, Rafael Stern, and Rafael Nishimura.
I think it's wrong, but it's all right.
That proves formally the following thing. If, as in standard theoretic Bayesian statistics, you frame your decision problem as a two-person game, the nature is the first person, and the scientist, the statistician, is the second person trying to win the maximum of information from nature in an experiment, in a statistical experiment, then you can argue, like you are doing, that, well, any sample is a sample, If I know the likelihood function, I can do inference. Okay. But in this paper, they show the following. If you frame the whole thing as a three-person, in a three-person situation, nature, scientist, and a third person with vested interests trying to influence the outcome of the experiment one way or the other, like the yoga physician that has the vested interest in showing that yoga is more effective than medicine, or the pharmaceutical company that is interested that yoga is good for nothing. What you should really do is to take the medicine they make. Then there is a huge problem. And the only known way to immunize the experiment against this, the influence, the evil influence
nature.
Of this third person.
Against nature.
Against the third person with the evil guy with vested interest, is to randomize. It's a theorem. Don't argue, it's a theorem.
Okay.
So, what can we do? What we can do is what your advisor, Basu, told. You can do intentional sampling.
Yes.
But you have to leave enough randomization in there to be sure to accomplish this immunization. And we can do that.
Sure.
So why don't you accept?
Why do I have to do that?
Of your master, Basu, I don't understand.
Why
that.
do I have to do that? See, if I trust the doctors. Because we have only two doctors. We had only two doctors. I know them. So, exactly. I did not have any problem with them. So I trust them. And that's why we believe that we could do that. And the guy who do the yoga is a very good friend of mine. And in the other kind of yoga is the same. So I know them very well, very well.
Even my mother.
No, yeah, sure, that's right. So if you are in the experiment like a person working with the people, you don't have this, you know when you have to do that. But in this case, we don't have to have. All right.
Yeah. Can I just add to that? Something like the third person, he says the pharmaceutical companies or drug companies, there could be a fourth person who are the ethics people in the hospital. You know, you have to send all these trials through the ethical considerations, and some ethical considerations may ask you to allocate treatment which are more likely to be effective to more severe patients. So ethics may come into play as well as another factor.
I never thought about that. You know, I believe you can, when you have many people come at the same time.
Okay, yeah, that's the difference.
You can order,
yeah,
and change the order and see which one is better.
Okay.
This is something that say why you want to do global optimization if we can change the order and see what is the best order to go in my experiment. If I have everybody the same, I believe it's not as good as the global optimization. But you can do that. Anyway.
Yeah, so I said that because ethics has come into play quite a lot after 1955 Basu's, results, after 1978 Basu's results or something. Okay.
Thank you very much.
Any other questions, comments? No. So let's thank Carlos again.
Thank you.